Hello, this is Dr. Bauer. We're going to look now at chapters 2 and 3, or at least almost all the sections in chapters 2 and 3 of Triola's text. So first of all, a frequency distribution basically shows the various classes and the frequency of occurrence in those classes. So first of all, class is an interval of a number interval where the variable has been divided up into those intervals. And then there's some terms on this screen here that you need to know, but I'm going to give an example of these terms in the next slide. So if you just try to learn something from the definitions, but then you're going to see an example in the next slide. So first of all, it says lower class limits. They're the smallest numbers belonging to the classes. Now the classes are these intervals. So the lower class limit is the lower number at the beginning of the interval, and then the upper class limits are the largest numbers belonging to the classes. So they're the upper end of the interval. So you got a number at the lower end and a number at the upper end of each of those classes or intervals. Now, the class boundaries are numbers in between the upper end of a class and the lower end of the next class. So they're a boundary in between intervals used to separate the classes. And then class midpoints are values right in the middle of each of the intervals. So there'll be a class midpoint in each interval, which is halfway between the lower class limit and the upper class limit. And then the last thing is called the class width. And the width is just the distance between the lower class limit and the next lower class limit. All right. So let's look at an example, and this will help you see what we're talking about. Okay, so the procedure for constructing a frequency table is these 5 steps. Choose the number of classes you wish to use. Now, usually you'll choose a number between 5 and 8 because having fewer than 5 classes is too few, and having greater than 8 is too many. And that usually is between 5 and 8. So then to determine the class width, you take the maximum value in the whole data set, so whatever is the highest value in the whole data set, and subtract the lowest value, the minimum value, and then divide that by the number of classes that you wanted to have. So if you decide, I want to have 6 classes, you'll take this maximum value minus the minimum value and divide by 6. And then you round up to a convenient number. And you'll see what I'm talking about here when we look at an example. Then you're going to choose the minimum value as the first lower class limit, or a number just below that. And then you'll repeatedly add the class width to the first lower class limit to get all the other lower class limits. And then you'll find the upper class limits and then tally or count how many data values are in each class. So let me give an example. Okay, so let's say you have this set of data, 34, 23, 64, 49, all the way to these other. Now they're not put in any order. They don't necessarily have to be for doing this. All right, but let's suppose we want 6 classes. So you just decide, okay, I want 6 classes. That means 6 intervals, as you see here. All right, so the highest value is 75. If you look at this data set, 75 is your highest value. 23 is the lowest value. So 75 minus 23, that's 52. And then you wanted 6 classes, so you divide 52 by 6, and that comes out to about 8.67. But you say to yourself, well, I could round that to 9, or it's almost to 10. I could maybe say 10, and that way your intervals are 10 wide. 10 is a more rounded number. So let's say 10 for the class width. So it's not real precise here. There's some leeway. You could have used 9 or you could use 10, but 10 is often easier to, or what we are used to seeing for rounding numbers. Now, the minimum value is 23, so I could use a number just lower than 23. Let's say 20 as my first lower class limit. So you see that I have 20 here as my first lower class limit. And then the other lower class limits would be, 30, 40, 50, 60, and 70. I just add the class width, 10, to the first lower class limit, 20. So 20 plus 10 is 30, 30 plus 10 is 40, so you get your other lower class limits. And then the upper class limits would be 29, 39, 49, 59, 69, 79. And that's because you don't have any fractions or decimals in here. So it's 20 to 29 for the first class, 30 to 39 for the second class, etc. All right. So that gives you your class limits. And then you're just going to count how many fall in each of these classes. So there's one number that falls in the first class from 20 to 29, so the frequency there is 1. But there's 3 numbers that are in the 30s. I see 34, 37, and 39. So you count how many fall in each of the classes. And then there's 1, 2, 3, 4, 5 numbers in the 40s. And then 3 in the 50s, 2 in the 60s, and 1 in the 70s. So that's how to produce what's called a frequency table. All right, so you should be able to do this. You should be able to take a set of data and do this whole process. Okay. Now, another type of table or aspect of a table is called making a relative frequency table, or putting relative frequencies into a table. And so relative frequency means the frequency for a class divided by the sum of all the frequencies. And then you can change it to a percentage by just multiplying by 100%. So, for example, for the class 20 to 29, there was one number in that class, and then you divide that by 15, because 15 was the total number in the whole set of data. There were 15 numbers, okay? So you go 1 divided by 15, because 15 is the sum of all the frequencies for all the classes, or it's the total number of numbers. So 1 divided by 15, and you get 0.067. But if you multiply that by 100, you move the decimal place over 2 places, you get 6.7%. So that's the relative frequency for the first class. Now, the second class, 30 to 39, had 3 numbers in it. So you divide 3 by 15. You're always dividing by the total of 15 for this situation. And 3 divided by 15 comes out to 0.2, and that converts to 20%. In the class from 40 to 49, there were 5 numbers. So you divide 5 by 15, and you get 0.3333, and that converts to 33.3% as a percentage. And then the next class was 3 numbers, so 3 out of 15 is 0.2, and you get 20%, etc. So that's how to complete the relative frequency table. And it's basically showing what percent of the scores are in each of the classes. So 33 1/3, which is about a third, 1/3 of the scores are in that middle class of from 40 to 49. Okay. Now, if you totaled up the relative frequencies in the middle column here, it would equal 1 approximately. Or if you total up these percentages in the last column, it would be equal 100% approximately. Now, why am I saying approximately? Because sometimes when you have rounding occurring, you've rounded some of these numbers, it may not exactly equal 100%. So it might be totally off, but it should be approximately equal to 100% when you add them up. Now, frequency tables are used to make histograms. We want to make, our ultimate goal is to take a frequency table and make a histogram. Now, a histogram is a graph made by bars of equal widths drawn adjacent to each other or touching each other. You notice there's no gap in between the bars. In a bar graph, you would have gaps between the bars, but in a histogram, there should be no gaps between the bars. The bars should be touching, unless you had a class or an interval where there was nothing in it, so they wouldn't have a bar there. But the horizontal scale represents classes or the intervals of the quantitative data values. So it's from 19.5 to 29.5, or from 29.5 to 39.5. So those are the intervals. The vertical scale represents the frequency of occurrence. So that was those frequencies that we had in our frequency table. That's always the case in a histogram. A histogram is the classes along the x variable or x-axis, along the bottom axis, and the frequencies or the relative frequencies along the vertical. All right. Now, here I'm using what are called the class boundaries. The boundaries are the numbers in between the first upper class limit and the next lower class limit. So between 19 and 20, which is 19.5, or between 29 and 30, so 29.5, etc. We could have also used just saying, from 20 to 29, 30 to 39, 40 to 49, etc. So let's look at an example of this. So let me move my video so it's not blocking anything. All right, so this is actually real data. This is murder rates per 100,000 people from 2012 for the 50 United States. So you have 50 pieces of data because there's 50 United States. And these are how many people are murdered per 100,000 people for the different states. Now you notice that a lot of them are 1 point something, then 2 point something, 3 point something, etc. But there is one that is away from the others, 10.8. 10.8. That's a high murder rate. I don't know if anybody knows which state in the Union has that 10.8 number of people killed per 100,000 people. Want to take a guess? Well, it's Louisiana. I don't know why, but Louisiana has the highest murder rate. Anyway, create a frequency table using the steps outlined in the notes above. So we refer to those steps. And so what I did here is I took the lowest, or I'm the highest minus the lowest, so 10.8 minus 1.1, it gave us 9.7. And 9.7, let's say I want to have 6 classes again. 9.7 divided by 6 is like 1.6 or 1.7, but I rounded it up to 2. So the class width I wanted to be 2 here. And so I didn't round down from 1.1 down to 1. I actually went all the way down to 0 for the first class, lower class limit. So I've placed my first lower class limit at 0, and then my next lower class limit was at 2, and then 4, and then 6, and 8, and 10. Notice you just add the class width that you want to the first lower class limit, and that gives you the next lower class limit, and then the next one, and next one, next one. Now, because these are decimals, like 1.1, 1.3, I needed my upper class limits to end at 1.9 or 3.9 or 5.9. Basically, it's the decimal value just less than the next lower class limit, which would be 1.9, or 3.9 is just less than 4.0, 5.9 is just less than 6, etc. So that gives me my class limits, okay? And then I just counted how many fall in each of those classes. From 0 to 1.9, there's 1, 2, 3, 4, 5, 6, 7, 8. There's 8 values from 0 to 1.9, and that's where I got that one. And then there's 14 from 2.0 to 3.9. I counted all these 14 values all the way to 3.9, and there's 14 of those. And then from 4 to 5.9, there's 19 of those numbers. You can count them. And then 8 in the next class, there's none in the class from 8 to 9.9. There's that gap in the data. And then from 10 to 11.9, there's 1. Okay, so now I make my bars to be equal to the height of occurrence. So in the first class limit, it's a frequency of 8. So my bar will go up to about up to 8. Okay, all right. And then the next bar is right up next to it, touching, and it goes up to 14. And then the next bar is up to 19, and then the next bar is up to 8, and then there's no bar in the class interval from 8 to 9.9. Because there was no occurrences in that interval, but then there's 1 in the last class. Okay, so that is how to make a histogram. You might have a gap, but there's no data, but just, move over 1, but still have that class. Don't, not put it there. You should still have the interval along the x-axis. All right. So when you're creating histograms, the shape of the histogram is something that we're going to be talking about. So I wanted to talk about various possible shapes. There's lots of shapes, but these are commonly occurring shapes that you'll see in statistics. The first shape is what's called a uniform distribution, which doesn't mean exactly the same across the board, but it approximately is the same across the board. And so you see in the shape that they're all, the height of the rectangles is all about the same. So there might be some variation in the height of the rectangles, but pretty much it's a line going across where the rectangles are all about the same height. Now if you have numbers that are just random, you randomly pick numbers from 0 to 9, for example, then, if they're purely random, you're going to have that uniform distribution where every one is about equally frequently occurring as the rest of them. Now, unimodal, a mode is like a high point. So unimodal means there's a one mound or one high spot in the data. So you see this is the height of males in a class and the frequency of occurrence. So this middle height is most populated, most frequently occurring, somewhere about I think the most common height for men is something like 5'10", and then after that it diminishes. So that's one. Now the next histogram here shows one that's approximately normal. A normal distribution is one that starts low, rises up, and has this shape, and then comes back to low. And this is what we call approximately normal distribution. Now the first histogram here, the heights of the males, is approximately normal, but not as normal as the next one, the second one, just because the shape is, it should look more like this shape. We'll talk more about the normal curve later. Now, bimodal distributions have two high points. All right, they're two raised mounds, and that would occur if you're dealing with the heights of all students in the class, both males and females. The reason is males generally have taller heights than females, and so the females would be causing this first mound, and then the males would be causing the second mound. All right. There'll be that bimodal mound if when you have the heights of all students in a mixed gender class. All right. Now, symmetrical means that when the left and the right sides of the distribution look the same. Now, all of the distributions that we've looked at already, the uniform distribution, which is straight across, the unimodal one, and the bimodal, they're generally have been symmetrical, the same on both sides. Okay, but a skewed distribution, like down here at the bottom, now this is unimodal. These pictures at the bottom are unimodal because there's one high point in both of these skewed left and skewed right distributions, but it's not symmetrical because this has a tail going off to the left, so we call that skewed left, and the one on the right has a tail going off to the right, so we called it skewed to the right. So you base it on which direction the tail, the long tail, goes to. All right. So skewed left or skewed right are other shapes of distributions that you might see. All right, so now we're going to look at Chapter 3 material, which starts off talking about measures of center. Now, sometimes it's unclear which is the best measure of center to use for a given set of data. Measure of center means what number value would best represent the center of the data. And we start off talking about the mean, or the arithmetic mean, or also normally called just the average. Average and mean are the same thing in statistics. So the average of a set of data is one way to measure the center of the data, or the approximately where the middle of the data is. So a population mean uses data from all individuals in the population. Now the equation is mean equals the sum of all values over the number of values. And this is the symbolism. This Greek letter is mu, all right, mu, or mu, and it looks like a U but with an initial tail to it. It's equal to the sum of all the x's, so that symbol there means sum of all. So we're adding up all the values and then dividing by how many there are in the population. Okay, so you got to know all the values in the population, and you got to add them all up and divide by how many there are. So that's just the average. I mean, that's what we know average is, adding them all up and dividing by how many you have. Okay, now that's in reference to a population. But sometimes we don't know the whole population, and we're only dealing with a sample. So in the case of a sample, it's the same equation. We add them all up and divide by the number of them, but we don't call it mu. We call it x bar. So whenever you see x bar, an x with a bar over top it, that means the sample mean. All right. We're talking about the mean of just a smaller subset of the population that we call the sample. And the formula is the same idea, the sum of all the x's divided by the number of them. But we use a lowercase letter n to represent the number in a sample. The capital N was for the number in a population, but lowercase for the number in a sample. So x bar is equal to the sum of all the x's divided by n, the number in the sample. All right, and x's are the scores, the individual data scores that we're talking about. So x bar is the mean of all those x's in the sample. All right, then the sample mean, however, is highly influenced by outliers or extreme values. So in other words, if you happen to get an outlier or a very high value or a very low value in your sample, it can throw off your mean. And that's just, the case. I mean, think of if you were in a neighborhood and you're talking about the average income in your neighborhood, but let's say Bill Gates moves into your neighborhood. Your average income in your sample will increase greatly if Bill Gates moves in. All right, it'll jump up the average income of the neighborhood, as you would expect. And that's the example here. Millionaire moves into your neighborhood. What happens to the mean income? It's going to increase a great deal. So we say that the mean is not resistant to outliers or extreme values. It's not a resistant measure of center. But the median, however, is resistant. So let's define what the median is. The median is the middle value when the values are ordered from lowest to highest. So after arranging the data from the lowest to the highest, if there's an odd number of values, then you choose the data value exactly in the middle. Okay, so the median is the middle value. So if there's an odd number, then you're just going to choose the one right in the middle. And so here's an example. By the way, we use the symbols an X with a squiggly over it, or I usually use the capital M because I don't want X bar confused with the median X squiggly. Let's just use capital M for the median. So for the data set 3, 5, 7, 8, 8, 9, 9, 9, 10, the median would be 8 because this second 8 right here is right in the middle of the data. It's the fifth value. So there's 4 values below that and 4 values above that 8. So 8 is called the median. All right. So now, what if there was a total number of values that's an even number? So there's an even number of values. Well, then you don't have a 1 right in the middle. Like, for example, this set right here, 3, 5, 7, 8, 9, 9, 9, 10. So I've removed an 8 from the middle of this data set. So let's say the data is this second set. Well, then you don't have a middle value. You got the 4 here and the 4 here. There's no middle value. Well, in that case, you're going to average the 2 that are in the middle. So 8 and 9 are in the middle here. So I'm going to average 8 and 9, and I get 8.5. All right. So that's how to handle finding the median. Now, the median is resistant to extreme values since 1 or 2 outliers will not change the median value by much at all. Okay, note that it is always the case that about 50% of the data values are below and 50% of the data values are above the median, because the median is the middle value, so it should be about 50% below and above the median. All right. So suppose we have the data set 5, 7, 9, 9, 11, 12, 14, 15, and 17. Find the mean and find the median. All right. Well, the mean, we're going to add those numbers up. So go ahead and add them all up and divide by how many you have. You have a total of 9 values. So add them all up and divide by 9. Okay, so if you added those values up, you should have got 99. And then if you divide by 9, because there's 9 values, you should have got a mean of 11. All right, so the mean should be 11 of the original set. Now, the median, if you look at the values, 5, 7, 9, 9, 11, so there's a total of 9, so the middle number is 11, so the median is also 11. So the mean is 11 and the median is 11, all right? So sometimes that happens. So now I say, suppose we add the number 51 to this set. So now do the mean and the median with adding the number 51. All right, so if you add up all the numbers, so it used to total 99, and you add the number 51 to it, it's going to total 150. So the sum of all the numbers now, with 51 included, is 150. And I have to divide that by how many numbers there are. So there are 10 numbers. So I divide 150 by 10, and I get 15 for the mean. So the mean has jumped from 11 up to 15. The median, however, when I put 51 on the end of this data, and notice I've got to have them arranged from lowest to highest. If I put 51 on the end, so now the middle numbers are 11 and 12, because there's now a total of 10 numbers, so that's an even number of numbers. So I've got to average the two in the middle. So 11 and 12 are in the middle, and if I average 11 and 12, I get 11.5. So the median has moved to 11.5 from 11, so now the median has changed from 11 to 11.5, so that didn't change very much, but the mean jumped from 11 up to 15. And so that's a significant jump. So you see how the mean is not resistant to outlier or high value, but the median is pretty resistant. It doesn't change very much. So now let's look or talk about the mode. So another measure of center, of where the center of the data is the mode. Now this means it's the most frequently occurring number. That's what the mode is. The data value that occurs the most frequently. Now, if two values both occur with the same high frequency, so let's say a number or two different numbers both occur 10 times and no other numbers are any higher than that in occurrence, well, then we say that it's bimodal. You have, both of those numbers to be modes, so it's bimodal. You could have it being trimodal, or having multi-modes, like 3 modes or 4 modes. But if no value occurs more than once, if all the values are not repeated, then you'd say that there's no mode. Like, for example, the usual number of children in a family is 2 children. Now that's the mode. It's the most commonly occurring thing. But you wouldn't say the average number of, or the usual number of children in a family is 2.1. I mean, because the actual average of number of children in a family in the United States is 2.1. But, that sounds weird to say the average number of children in a family is 2.1, because you can't have a decimal of a child. So we just say the usual number of children in a family is 2 children, the most commonly occurring value. Now, another measure of center is the mid-range. It's a value exactly halfway between the maximum and the minimum values. The equation is mid-range equals maximum plus minimum divided by 2. But we don't usually talk about the mid-range in statistics because it's only based on 2 values, the lowest and the highest. So it's not a very useful thing. All right, let's move on. Now, as far as calculating these measures of center, the mean, the median, the mode, all that, here's some round-off rules. for the mean, median, and the mid-range, you're going to carry out your calculations and round these values to 1 decimal place beyond those of the original data values. So here's an example. Let's say you're having the average 3.4, 3.7, and 4.5. So if you add them up and divide by 3, since there's 3 numbers, you get a mean or average of 3.8666666 repeating forever. So how far do you round this to? Well, because the numbers started off rounded to the 10th place, when we round the mean, we're going to go to the next place beyond that. 1 decimal place beyond how the numbers were rounded originally. So 3.87. So I'm going to round this to 3.87 because these were to the 10th place. The original numbers were to the 10th place, so I want to go to the 100th place for my mean. Okay, that's an example. Now, examples 6 and 7 on pages 97 and 98 of the text are important for your understanding when it even makes sense to find measures of center or to combine 2 measures of center. So look at examples 6 and 7 on pages 97 and 98 in the textbook. But here's another example that I've made up for this. Example, suppose you and another student scored a 76 and an 80 on a test, or it was an average of 78. So you and another student have an average of 78. Now suppose all the other students in the class are the numbers 60, 64, 72, 74, and 80, and all of those averaged out to 70. So you and another student had an average of 78, but all the other there's 5 other students in the class, and they had an average of 70. If I wanted to know what's the average or the mean for all of the students in the class, the 2, you and that other student, plus the other 5, could you just take the numbers 78 and 70, the average of those 2 groups, and average them together and get an average of 74? Well, the answer is no, you cannot. Okay? The reason is that the sizes of the groups aren't the same. The 2 students, you and that other student, is a group of 2, while the other group is a group of 5. So because they aren't the same size groups, you can't just average the 2. So it's natural to think that you can just average the 2 averages of 78 and 70 and get 74, but this is incorrect. The actual average, if you add up all those scores, 76, 80, 60, 64, 72, 74, and 80, and then divide it by the total number, which is 7, you get 72.3. So you see that you can't, if the sizes of the groups aren't the same, you can't just average the averages. All right. Now, what do you do if you have a frequency table, and you want to find the average of the data? Okay, so calculating the mean from a frequency distribution without knowing the actual data set. So look at this table here at the bottom. So let's suppose that you had these classes 20 to 29, 30 to 39, 40 to 49, 50 to 59, 60 to 69, and the frequencies of occurrence in those classes are 2 for the first class, 4 for the second class, 7 for the third class, 6 for the fourth class, and 1 for the fifth class. So all you have is the frequencies and the class intervals, all right, or class limits. How can you calculate the average value from that? Well, this is how. You're going to first, it says, to find the mean, you must first find the sum of all the values and divide by the number of values. Since you do not know the values, you can use each class midpoint as an approximation for each of the data values in that particular class. So you can just multiply each class midpoint by the frequency. So, okay, so in other words, I'm going to find the class midpoints and multiply it by the frequencies, all right? And so the formula is the sum of all the products of the frequencies and the class midpoints, and then divide that by the sum of all the frequencies. So let me get my marker and I'll do that. All right, so what I've done here is calculated the class midpoints. Now you can do that by adding up the lower and the upper class limits. So 20 plus 29, you get 49, and then divide that by 2, because there's 2 of them. You know, the lower and the upper, you add them up and divide by 2. So 49 divided by 2 is 24.5. For the next midpoint, you can divide 30 plus 39, which is 69. 69 divided by 2 is 34.5. And then 40 plus 49 divided by 2 is 44.5. 50 plus 59 divided by 2 is 54.5. And then 60 plus 69 divided by 2 is 64.5. So you can see that these differ just by 10 because that's the class width, but these are the class midpoints: 24.5, 34.5, 44.5, 50, etc. All right. And then what I also did is I multiplied the midpoint times the frequency, because we have to form these products of frequency times midpoint. So 2 times 24.5 is 49. 4 times 34.5 gives you 138. 7 times 44.5 gives you 311.5, etc. All right, I'm just multiplying the midpoint times the frequency to get the FX column. All right. Okay, so once you get the FX column, then you add up the FX column, and so I got 890 for the sum of that FX column. And then you also sum the frequency column, so you add that up and you get 20. And then the final calculation for the mean of all this data approximately is 890 divided by 20. So my total of my FX column, 890, divided by the total of my frequency column, which is 20, which basically this 890 is an approximation for the total sum of all the data values, divided by 20, which is the number of data values. And that's really what the average is, the sum divided by the number of them, and you get 44.5. Now it's just a coincidence that we got the same mean as the midpoint of the middle class. It just happened to be that way. But the mean for all this data is 44.5. All right, so next section we're going to look at is measures of variation. Now, we've already looked at measures of center, but now we're going to look at measures of variation. Variation means how widespread the data is, how much variability or variation there is in the data. All right, look at the 2 histograms. Suppose that when a teacher gives a test, the scores on the test, if I made a frequency table and then made a histogram with those scores, they look like this. Okay, so they're unimodal. They're all approximately around the middle value here. And so that's what the math test scores look like. But suppose then a history teacher gives a history test and the scores on the test, and you make a histogram using the same intervals, but the scores on the history test were like the second histogram. So obviously the math test scores were closer together than the history test scores. The history test scores show a wider variability or a wider spread in the data. All right, they're more widespread. You have more lows and more highs, and they're more spread out. So we say that second test, the history test, has more variability or spread. All right, so how do we measure variability or spread? Well, there's a few different ways. The first way is called the range. Now the range only uses two scores, the highest and the lowest, and you just go the maximum minus the minimum score. All right, so it's easy to calculate, but it's only based on two scores, so it's not a very good measure of variation. Usually you want to measure variation based on a lot of scores, not just the lowest and the highest. So another measure of variation is called the standard deviation. Now, standard deviation has got to be the most important measure of variation in all of statistics. It's used most often to measure variation. All right. Now, the standard deviation could be thought of as an approximation for the average deviation that scores are from the mean. Now, deviation means difference in, or how much it deviates from the mean. And to calculate the standard deviation by hand, I have this example here, but the formula for standard deviation is the square root of the sum of all these what are called deviations squared divided by n minus 1. All right, n being the number of scores. So let's show a by hand calculation of the standard deviation. Now you won't have to do this usually, but I wanted to show the by hand calculation to see where how this formula works, where things come from here. All right. So suppose you have the data 2, 4, 5, 8, and 11. So that's your data. You've got 5 scores. So if you add up those scores, it adds up to 30. So 30 is your sum of all the numbers, and you divide it by 5 because there's 5 numbers, and so x bar is 6. X bar is the mean or the average of the sample. So 6 is your average of the sample. All right. So x bar being 6, what we do is the deviation for each one of them. So the scores are 2, 4, 5, 8, and 11, but we do the deviations. That's that second column. So we go 2 minus 6, negative 4. 4 minus 6, 5 minus 6, 8 minus 6, 11 minus 6. So we're always taking the score minus the mean, which is 6. All right, for all those data. And then in the next column, we're going to square that. So the score minus the deviation squared. So 2 minus 6 is negative 4. Negative 4 squared is 16. 4 minus 6 is negative 2, but you square it, it's positive 4. 5 minus 6 is negative 1. Squared is positive 1. 8 minus 6 is 2. Squared is 4. 11 minus 6 squared is 25. So these are the squared deviations. Now notice the deviations were negative in some cases, but you squared them, so you end up with always positive squared deviations. Okay? So the sum of all those positive squared deviations is 50, and so the formula tells you to take the sum of all those deviations squared. So we did that already. We got 50 for the sum of the squared deviations, so that's the numerator. And then there are 5 scores, so 5 minus 1 is your denominator. That slide slightly. I deleted the item at the far right here that you see my cursor near, the 250 over 20. But just, the sum of all those was 50 divided by 4, because 5 minus 1 is 4, and 50 divided by 4 is 12.5. And so we got to take the square root of 12.5, and you have 3.54. So that was the correct value for the standard deviation using the by hand method. All right. So we're going to have a way that is the calculator method that does this all for you, but I just wanted to show you the calculations for the standard deviation. Now, do you see, I hope, from this, how we're averaging, approximately averaging the deviations, Now, we squared the deviations, but then afterwards we square rooted, took the square root of the whole thing, so they sort of can't, the squaring and the square rooting sort of cancel each other out. So it ends up being basically the average of the deviations. Now, we did make a little bit of adjustment by dividing by n minus 1 instead of dividing by n, but that's just part of the formula for standard deviation for a sample, and I don't want to take time to explain that right now. But that's the by hand method, and you should be able to maybe do that on a quiz, but maybe not. I might not ask it for an exam because we'll use the calculator for most of it. Okay, so the calculator method involves using the data editor. So what you do is you press stat, so you hit the stat button, and then you choose the edit item. So it's the first one in the list. So press stat and then edit, and then if you have data in your L1 column, you can delete that by going up to the heading of that column where it says L1 above, in the heading, and then hit clear and then enter. Now don't hit delete. Hit clear, not delete on your calculator, but clear and then enter. All right. If you've accidentally hit delete, then you got to do the setup editor. You got to go stat and then choose setup editor and do that until it says done. But it's best just to go up to the heading of L1 and hit clear and then enter. Now, then you go down and enter the data into L1. So put all your data into L1 and then make sure that you have the correct number of items and that they're all correctly entered. And then you press stat and choose the calc item. So you got to move over to the heading or the pull down menu called calc, and then you're going to choose the first item there, one variable stats. Okay, now when you press one variable stats, it's going to send you to the home screen, and then it'll write the one variable stats command there, and then you have to press enter again to calculate. All right. Now, if you want L1 data to be calculated, one variable statistics to be done with the L1 data, just press enter because that's the default. But if you want some other column like L2 or L3 or L4 or something like that, you'll have to type in the name going second and then the number 2 or 3 or 4 to get the L2, L3, or L4. All right, but anyway, so just hit stat, calc, and then go to one variable statistics and press enter, and it should calculate your one variable statistics. Now it will give you what the mean is, which is your X bar, and as well as the sum of all the scores, delta or sigma X, and then the sum of the squared scores, and then you'll see the standard deviation, SX. And that's what we're looking for. Standard deviation, SX, is the same as what we just calculated by hand. All right? Now, SX is the sample standard deviation. All right? Which we have the letter S to signify. There's also what's called the population standard deviation, and that's sigma X. This is the small case sigma. Sigma X is the population standard deviation. The formula does not use n-1 in the bottom. It uses just capital N, which is the population size, or the number of scores in the population. So population standard deviation has a slightly different calculation, and it's sigma X, not SX. But usually we'll be in statistics, we'll be using SX, the sample standard deviation. Now, some facts about the standard deviation. First of all, the more widespread the data is, the higher the standard deviation is going to be, because standard deviation measures the spread of the data. If all the data is the same, if your numbers are all the same, like if your data set was 5555555, all right, that's your data set, then the standard deviation is going to be 0 because there's no deviations from the mean, all right? But that's the lowest it can be. Standard deviation can never be negative, all right? Your standard deviation should never come out to a negative number. If your data is all the same, the lowest it can be is 0. Now, letter B here, the standard deviation is not resistant to extreme values and changes dramatically when an outlier is introduced. So if you add a very large or very small number to your data, it's going to really change your standard deviation. It's important to realize this fact. Now, the sample standard deviation, though, is considered to be an unbiased estimator. And what that means is it accurately targets the population standard deviation. So if you take a sample and calculate this sample standard deviation, SX, that will be pretty close to the population standard deviation, all right? And so that's why the sample standard deviation is really useful in statistics, because it helps give us a good estimate for the population standard deviation. Now, the quantity n-1 in the calculations, remember we divided by n-1? That n-1 is called the degrees of freedom. And it's because if we know the mean, there are only n-1 data values that can independently change. The very last one cannot, because if the mean is fixed, that value is going to be fixed. So there's actually n-1 independent degrees of freedom. But if you don't understand that, don't worry about it. It's just a quick explanation why that's called degrees of freedom. Now, the variance of a sample or variance of a population is simply the square of the standard deviation. You can find the standard deviation using the calculator or the by hand method, but then just square it, and that's the variance. So some facts about it: just like the standard deviation, the variance is highly influenced by extreme values. The variance is never negative, and the variance will be 0 when the data values are all the same, just like the standard deviation. The symbolism, here's a summary of it. S, or SX, is the sample standard deviation. S squared will be the sample variance, the square of the sample standard deviation. So S squared is what you should think of when you hear the word variance. Sigma is the population standard deviation. Sigma squared is the population variance, or the square of the population standard deviation. All right? So keep in mind those things. Your variance is just the standard deviation squared. Now, the last thing in this section, they start to talk about the normal curve. Now, normal curve is very important in statistics. It's one of the key ideas. To be a normal curve, it's informally called the bell curve, but to be a normal curve, it has to have a very specific shape. Okay? If it has this specific normal curve shape, then 3 facts are true, and this is called the empirical rule for the normal curve. All right? The first fact is that about 68% of the data values will fall within 1 standard deviation of the mean. So the mean is right here in the middle. The normal curve is symmetrical. It's the same on both sides, and the mean will be right in the middle. Okay? Now, if you move one standard deviation down from the mean and one standard deviation up from the mean, those two boundaries will enclose 68% of the scores. So 68% of the scores, approximately, will fall within one standard deviation down and one standard deviation up from the mean. Okay? Not exactly 68, but about 68. Now, two standard deviations, rule number 2 says about 95% of the data values will fall within 2 standard deviations of the mean. That means if I go down 2 standard deviations and up 2 standard deviations and set my boundaries at those 2 points, then 95% of the scores will fall in between those values. Okay? So 2 standard deviations down and 2 standard deviations up from the mean, that will enclose 95% of the scores. And then the third rule says that if you go 3 standard deviations up or down from the mean, that will enclose 99.7% of the scores. So almost all of the scores are within, excuse me, are within 3 standard deviations of the mean. All right, so I hope that's clear. Only 0.3% of scores are outside of 3 standard deviations from the mean, either down or up. All right, so I hope that you've been able to digest this material. We are starting to teach some of this material in Math 120 course. You may or may not have had this material in the Math 120 class, depending on when you took it, but hopefully you can study this material and be able to apply it in the homework. Of course, give us a call or email if you have any questions. All right, thank you.